Hi, my name is Michael Coughlin, and I'm a professor of physics and astronomy at the University of Minnesota. Um, I am a member of the LIGO Scientific Collaboration and work in the Zwicky Transient Facility. Um, and the talk, my title is Machine Learning in the Multi-Messenger Era, which is a grandiose title that there's no world in which I'm going to do justice to in 15 minutes, and so I'm going to try to give a brief overview of a number of ways in which machine learning has changed how we're doing this aspect of astronomy. And as a member of LIGO, I am, of course, very interested in compact binaries and their multi-messenger counterparts. And so the vision here is you have two compact objects. Often we have two black holes, but sometimes we have at least one neutron star. And these compact objects are inspiraling around one another, emitting gravitational waves, and eventually merging. And in the case where you have at least one neutron star, you produce a gamma ray burst, where you have this very highly energetic set of photons that are highly beamed, and if you're lucky enough to be in their path, you will see this burst of gamma rays. Now, the material that is ejected from this system, which is undergoing our process nucleosynthesis and generating these heavy elements. So this ejected matter produces astronomical transient known as kilonovae, and it is these objects for which we'll be focusing on for a part of this talk. Now, there's a lot of different areas of physics that you can cover with these bineutron star or neutron star black hole mergers. For example, there's tension in the physics community over what the expansion rate of the universe is. Depending on the measurement method, you get different answers, which could either indicate potentially some kind of systematic that's not understood in the measurement, or potentially new physics. And so gravitational waves are yet another measurement that may provide insight into this really interesting area. They also provide insight into the equation of state of neutron stars. These neutron stars are really incredible laboratories to study some of the densest places in the universe outside of something like black holes. And so you can probe using observations of these neutron stars what is going on, for example, near their core. Last but not least, GW 17817 really changed how we think about testing general relativity. So the fact that we had photons that were just 1.2 seconds after the gravitational waves arrived set really, really stringent limits on a variety of theories of alternative theories of gravity. And so it's yet another place that really is changing physics. And so the point is these multi-messenger detections are really huge drivers for the science with these compact objects. And so unfortunately, there's, the path from gravitational strain to, the science that I just mentioned is a long and arduous journey. And so in general, you start with this gravitational wave detector strain. You need to clean it, you need to calibrate it, and then you need to detect the gravitational waves. From there, you need to localize them onto the sky. Unfortunately, gravitational wave detectors are not great at localizing things. And so, as you see on the left-hand side, you can have to look over thousands of square degrees sometimes to look for these optical counterparts. You want to classify the objects as to whether they have a neutron star or not, and then you need to alert the astronomers. From there, they take images, they find candidates, they do follow-up photometry and spectroscopy, and thereafter hopefully identify and characterize the system. And so we'll talk about a few ways in which machine learning is really changing how we think about some of these steps. So first of all, in terms of cleaning the gravitational wave strain, gravitational wave detectors are very sensitive instruments. and therefore they are very susceptible to the technical environmental noises that prevent the detectors from operating at their design sensitivity. Noise coupling, such as, for example, the ground motion or magnetic fields that are on site. Unfortunately, the way these couple in are often unknown, and potentially the coupling is nonlinear, which makes it difficult for more traditional methods. And so recently, these machine learning methods have been pioneering how to take advantage of on-site auxiliary sensors, such as seismometers, magnetometers, to predict the detector noise, detector response, and remove the noise. And there's a dedicated talk on this at this conference. Similarly, these non-Gaussian noise transients are the limiting noise source for our ability to detect gravitational waves. And so, unfortunately, many of these noise sources are not well understood. And so the tactic that's been taken is to create this large-scale Zooniverse-based labeling program called Gravity Spy that's been used to label many thousands of these transients, with the idea that you can use machine learning methods to probabilistically classify both the known noise source classes, but also identify new ones. And so thereby make it possible to make these gravitational wave searches more sensitive. Speaking of these searches, the concept of doing optimal detection using what we know from general relativity has been known for a long time. There's many methods relying on matched filtering out there, but unfortunately, these statistics tend to be optimal in the case where you have Gaussian noise, in which gravitational wave detector simply is not. And so machine learning has some advantages. For example, you can train on data sets that have both these large sets of noise transients that I just talked about, as well as simulated gravitational waves in order to train the algorithms. And so recently it's been found that these algorithms are not only fast, as many of these machine learning algorithms are, but also potentially more robust to some of these data transients. And so they're very promising. But it's not enough to have just detected the gravitational waves. And so, so while the gravitational wave detection is very fast, the gravitational wave inference, or the estimation of the parameters such as the masses, the distance, the sky location, etc., tends to be slow, on the order of hours to days. And this is because you're comparing your gravitational wave detector to hundreds of thousands to millions of these waveforms. Fortunately, machine learning methods have been used recently to show that you can infer source parameters up to something like 1,000 times faster, which, if they are able to be applied to the signals of interest here, i.e. those that contain neutron stars, would really revolutionize how we think about doing follow-ups. Similarly, again, we are interested in looking for objects that have at least one neutron star present. Unfortunately, in the case where you're just interested in gravitational wave detection, all you know is the template or the waveform that happened to fit it best, and you can kind of measure let's say, the total mass of the system reasonably well. Unfortunately, this throws away the fact that there's a relatively large uncertainty on, for example, the mass ratio of the system, what its equation of state is, and everything else, which will inform, the likelihood that you have a neutron star or a black hole present. Fortunately, we can use these machine learning methods trained on large simulation sets, where you know the true value and can compare it to the best fit template to properly assess the uncertainties especially in the masses that are found. And this has been instrumental for giving accurate predictions for the likelihood that you have a neutron star present, and therefore are beneficial for follow-up or not. Similarly, it's not enough to know that you have a neutron star present. You really want to know, what is the likelihood that I can actually go after and find this counterpart with my telescope. Conserving telescope time is a good thing. And so the main issue here is that these kilonova light curve models, they're typically computed on high dimensional grids, and so they can be quite difficult to accurately interpolate and do inference across the entire parameter space. And so there, again, machine learning methods have been used to overcome this. They're to interpolate the light curves across this parameter space and use the low latency gravitational wave inference to make predictions about what the expected light curves are. Moving ahead to more of the astronomy side. So in many ways, the analysis of astronomical survey data has similarities to the gravitational wave case. There are many bogus transients in astronomical images that must be dealt with. For example, you have what's known as bad image differencing, where you take your science image and compare it to a reference image taken sometime before to look for new objects. Sometimes those comparisons go very wrong. Similarly, if you have bright stars on your image, the charge in those pixels bloom and again create essentially bogus transients that you need to rule out. And so, of course, machine learning has been used to train on the image cutouts of both real and bogus objects to score these transients for their likelihood of being astrophysical. But even if you have a astrophysical transient, you're not sure if you should care about it. And so, for example, we know that we expect compact binary mergers to occur in galaxies. And so, unfortunately, stellar flares or flaring stars are a large potential contaminant to the searches. And so, recently, machine learning methods have been trained on pan-stars, flux and shape measurements, so it's yet another survey, combined with Hubble Space Telescope-based classifications to estimate the probability that the transient that you're looking at is based in a galaxy or based simply from a star. Moving ahead, so once you have your list of candidates, you'll often get spectra of them. And so, but it's important that, once you have spectra, you need to understand what that means for the type of transient you have. And so, especially in these times, there's an advent of relatively low resolution spectrographs. And so let's say the typical methods for doing spectral typing based on simply overlap with, known previous transients, just doesn't cut it. And so machine learning methods are being used to train on many of these previously classified objects to perform probabilistic classification for these low resolution spectra to accurately determine, do I have a supernova, do I have a kilonova, et cetera. So this was a very brief introduction into machine learning methods and how they're permeating every area of multi-messenger astronomy. I wanted to just briefly highlight this paper that was recently accepted. I think the lead authors did a very nice job talking about how gravitational wave science is being changed by machine learning. And so this is a place to go to understand where where the field's at and where it's going. And just to give my own brief perspective here, in terms of where I would like to see the field go. So for example, machine learning methods have been incredible for demonstrating that for binary black hole detection, parameter inference, which has been excellent, but those signals are relatively short. Can those same methods or what extensions need to occur for binary neutron star black hole signals, which are much, much longer? What will it take to get similar results? Similarly, there's been a lot of work on classifying astronomical transients just by their photometric time series. Most of these algorithms have been trained on, tested on, relied on the fact that they have many data points to fully characterize the light curve, whereas in the gravitational wave counterpart case, you're usually dealing with a sparsely sampled light curve that just captures a very, let's say, very narrow amount of time. And so, can machine learning methods provide follow-up strategies to help rule in and rule out these transients. Given that we do have limited telescope time, there are differences in sensitivity. You can either get photometry or spectra. What are the right choices to make here? Finally, as this is a multi-messenger talk, one of the great holy grails for this field is a true multi-messenger pipeline, which does inference on gravitational waves, optical data, gamma rays, etc. You know, the dimensions of this parameter space are very, very large, and so maybe machine learning is really the key to taking advantage of all of these diverse data sets.